So in section 11.4, we're going to discuss logarithms. And to try and motivate logarithms, I'm going to start by calculating the inverse of a couple functions. Now, of these two functions, f of x and g of x, which one of them is the exponential function? G of x. G of x is your exponential function. You've got a fixed base to a variable exponent. So our first step in trying to find the inverse of a function is to replace the f of x or the g of x by y. What's the second step? Does anyone remember? Thank you. Interchange x and y. So we'll get x equals y cubed and x equals 3 to the y. All right, good. Someone else. Now what? What do we do to try and find that inverse? Yeah, cube root on both sides. So we're trying to get y by itself. So I'll take the cube root of both sides. And that's going to simplify to the cube root of x equals y. That's your inverse function. So we'll call that f negative 1 of x. But you run into a problem over here when you try and do that for g of x. With what we've covered in this course so far, you just don't have something available to solve for y. So we're going to invent a new function, and it's going to be the logarithm. We're going to take the log base 3 on both sides. And that's going to give me my value for y. Y is going to be the log base 3 of x. And in fact, that's my inverse. G negative 1 of x is the log base 3 of x. So what on earth is the logarithm? Well, we're going to have to discuss that. Was that your question, or do you have something different? Yeah, when you go from a function to its inverse, yeah, the negative 1 here is going to denote that it's an inverse function. Now keep in mind, this is much different than the reciprocal. I'm not really fond of this notation that it's negative 1 there, because people want to take the reciprocal. They go, oh, f negative 1, that's 1 over x cubed. Yeah, but it has nothing to do with the reciprocal whatsoever. It's kind of frustrating and annoying that way. All right, but I appreciate the question. Thank you. Getting back to this, we need to understand what that really means. And to help out with that, we're going to go over a bunch of examples. So we'll take a look at our handout here. And I guess I would suggest that you highlight this part right here. Because if you have this memorized, and you write it on the top of your test right when you first get it, before you can forget anything, you write that down, then it's going to save you. It's going to get a lot of work done for us. But basically what this is saying is that these two things are equal. A to the y power equals x. So from the point of view of the log, you're going to look at the base here, which is your a, and ask yourself, what power of a gives me x? So a to that power gives me x. And the answer to that question is your y right here. So a to the y equals x. So let's look at that from the point of view of this first example. The question you can ask yourself when you're looking at this is, what power of 2 gives me 16? 2 to the 4th power. And equivalently, 2 to the 4th equals 16. So this is written with logarithms. This is written equivalently with exponents. But really, when you're working with logs, you're kind of thinking about exponents. And you can always double check your work here on these. You can take this to this power should be this. 2 to the 4th power equals 16. Let's try the one below that. What power of 4 gives me 16? 2. And equivalently, if you're to write it with exponents, 4 to the 2nd power equals 16. Now don't make too much about the symmetry here. There's nothing really much to read into that. Let's move down to the next one. What power of 5 gives me 125? 3. And like the previous couple, you should be able to rewrite this using exponents. It's this to this power equals that. And that's something you can actually check on your calculator if you wanted to. So equivalently using exponents, what would this one be? Thank you. 5 to the third equals 125. So you're always asking yourself, what power of the base gives me what's called the argument, which is where the 81 is. What power of 9 gives me 81? What power of 4 gives me 64? 3 and 70, or 3 and 81. So why don't you try the next, maybe 4. I'll give you a minute or two to work on that. See what you can come up with for those. And then after you figure out the answer here, try and write them equivalently using exponents. So give that a shot. Looking pretty good. A little spot check. So let's run through these. What power of 9 gives you 81? 2. And equivalently, 9 to the second power is 81. Let's keep going. How about what power of 4 gives you 64? 3. And 4 to the third power equals 64. This should always work out. It should always be this to this power equals this. And this is something you can check. It won't be a little while before we can check this directly on our calculators, but right now we can't exactly check this too easily. So it's nice that we can see equivalently that this one works. What power of 3 gives me 81? 4. So 3 to the 4 power equals 81. And last but not least, 7 to what power gives you 7? First power. 7 to the first power is 7. So nice. All right. Let's go a little bit farther. How about this next one? What power of 8 would be 1 over 8? Has anyone got that one? Yeah, way to go. -1. So, equivalently, remember it's always the base to this power equals this. What would that be using exponents? Cole, you want to give that one a shot? Perfect. And that makes sense because when you have a negative exponent, you can take the reciprocal and get rid of that negative exponent. So, well done. Now, as we think about problem number 36, let me ask you to think about the number 36 itself. Does anyone know anything interesting and useful about 36? Perfect square. Yeah, this is 6 squared. So use that or think about that as we're looking at, well, what power of 6 would give me 1 over 36? Or equivalently, what power of 6 gives me 1 over 6 squared? One more time. -2. Well done. Thank you, Taylor. So 6 to the -2 power is 1 over 36. Okay. Next one down is a little bit more challenging. What power of 7 gives me the square root of 7? You got to think back to our work with rational exponents. We did this, chapter 10? Go ahead, Zach. Yeah. So 7 raised to the 1/2 is the square root of 7. Square root is just another way of writing something to the 1/2 power. Remember a long time ago when we were doing rational exponents, I did the little boot method. I said, all right, draw a boot here, kicks the 2, 2 comes over, the 7 drops down. That gives you the square root of 7 to the first power. But something to the 1/2 power is just like a square root. Okay. How about an easy one? Log base 10 of 10. Not 2. 1. Yeah, the next one's 2, right? What power of 10 gives me 100? That would be a 2. Now with these, let me start sharing with you that you can do stuff on your calculator. So let's take a look at this on your calculator. Now a little confession or a little bit of notation to bring you up to speed on. Log base 10 of x. Quite often we're going to write that as the log of x. We're not going to bother to write the 10. It's kind of like the default. So just like we have a default when we're dealing with square roots, when I wrote the square root down here, I didn't put a 2 in front of that root. It's just understood to be there. Same thing with logs. If you write a log base 10, well, it's understood to be there. You don't have to write the 10. Now, there's more good news for us with regards to these logs, and that is you can calculate them on your calculator. So on the left-hand side, at least on the graphing calculators, next to the 7, there's your log key. Let's try log of 100. Not that we can't predict that one anyways. The log of 100 should be 2. Yay. So log of 100 is 2. That gives me 10. The second power is 100. The last one was 10 to the first power was 10. Now, a couple of the rest of these should be predictable. What power of 10 gives you 1,000? 3, and then 10,000, 4. Now, down here, they get a little bit more dicey. It's not quite as clear. So that's where you can use your calculator, right? Log of 0.01. -2. How about the log of 0.001? -3. Somebody do me a favor and write that one using exponents. Equivalently speaking, what would that be in exponents? All right. 10 to the -3rd is 0.001. Does that make sense? Does that look right? Let's tackle it this way. 10 to the -3rd is 1 over 10 cubed. Yeah, that's supposed to be a cube. What's 10 cubed? 1,000. And a 1 over 1,000 is 1/1,000. So it works. It fits. How you doing with logs? Are you getting more comfortable with those? All right. We'll tell you what. Let's work with logs the other way. We're going to start out with exponential equations and write them in logarithmic form. Now, at the start of this lecture, I suggested that you memorize this, because this is going to get you out of a lot of jams. Whoops, how come that blacked out? There we go. And here's one of them. if you're starting out with exponents and you got to write it in logarithms, let's just kind of copy this down here. A to the y power equals x, and that's going to be equivalent to log base A of x equals y. So when I go from one to the other, it's just a matter of lining things up. It's a matter of understanding, okay, well, what's the base? Well, the base in this case, A, would be what? A here is 10, A here is 10. Log base A of x, what's the value of x in this one? 1,000. And that equals y, which is your exponent, which is your 3. So log base 10 of 1,000 equals 3. What if somebody gave me just log of 1,000 is equal to 3? Should I mark them wrong? No, because it's understood that this is base 10. So you're okay with that one. Remember our notation earlier. Log base 10 of x is the same thing as log of x. You don't have to write the 10 there. It's understood to be there. It's a little more challenging going this direction. So are we okay with the first example? Thank you. Let's try another one. Let's try this one. It's again going to be log of some base. So log base what? 3 of x, which is 1 over 81. And what's that equal? -4. Nice. Keep in mind, you can also work these things backwards. You can double check yourself. Remember, this to this power equals this. Oh, that's exactly what I have over here. It should kind of recombine to go back from logarithms to exponents. So I'm going to give you a few to try. These last 3 here. Try and do the same thing with these last 3 that we did with the first 2. Oops. Go out the other way. There we go. Give that a shot. Okay, so this one, I want the log. The base is m. So when you write your base, make sure it's a subscript. It's below the level of the line where you write the log. Log base m of p. equals n, which is the exponent. So m to the n power equals p if you worked it backwards. But be careful with this because, if you wrote it a little bit differently, like log of m to the p power, that's something different. This suggests it's like log base 10 of m to this p power, and I get a little uneasy when I see that. So try and be careful to help us both out. That'd be great. Let's try the next one. Anthony? Perfect. Log base b of 2/3 equals r. And last one, Nick? Thank you. And thank you both, gentlemen. How are you looking on these? You starting to get okay going backwards and forwards between these? This is really predictable problems for the exam. I mean, these are an easy 4 or 8 points, depending on how many of them I put there. But just going backwards and forwards to exponential or logarithmic form. That's it. And there's even more of a bonus on that as well. If you're good at that, it can help you solve certain types of logarithmic equations. So let's see that. Let's see that with problem number 52. So log base x of 9 equals 2. Now, let me give you a heads up, a reminder. Maybe we should put it on your sheet here. This one in your handout. A has to be greater than 0 and different than 1. So when you're talking about the base of a logarithmic function, the base has to be a number greater than 0, but not equal to 1. A positive number not equal to 1. We'll keep that in mind as we solve problem number 52. Is greater than 0 and different than 1. Or x is greater than 0 and different than 1. So, well, the only trick we know at this point is to rewrite this using exponents. So, Sydney, what would this look like if I rewrote this using exponents? Start with the base. Equals, there we go, x squared equals 9. So, cool. Thank you, Sydney. What could x equal? 3. Now, technically, when you're solving an equation like this, x could equal plus or minus the square root of 9, which is plus or minus 3. But I just got done telling you that the base has to be positive. So if you forgot that there's, a plus and minus square root here, it wouldn't hurt you on this one because we can't use a negative one. The only solution that works is x equals 3. Okay, so we got done with one of them. That was a logarithmic equation. That's nice. Let's try problem 68. You know what? Actually, there's one I think I want to do before we do 68. Let me see if I can't find it. We will get around to doing problem 68. Let me just look for, I think it was 62. Yeah. So we're going to do 62 over here. Log base x of 0.001 equals -3. Well, we're kind of stuck in the same place we were before. And that is, we got x, which we can't get our hands on very easily, so then what? Jeanette, what would this look like if I rewrote this? Not squared. Start with the base, raised to that power. So x raised to -3 equals what? What would that equal? X negative 3 equals, anyone? 0.001. Okay. Now there's a trick in solving these things. I mean, you can solve it kind of like the long way, or you can solve it the short way, the most efficient way. And the most efficient way goes back to stuff that we've done before in this class, and that is to raise both sides to the reciprocal power of the exponent. So let me write that down here for you. Raise both sides to the reciprocal power of the exponent. So in this case, the exponent is negative 3. So, okay. Almost a trick question. Not really trying to be a trick question. But what's the reciprocal of negative 3? Now, the reciprocal doesn't change the sign. The sign is going to be the same. Negative 1/3. So I'll raise both sides to the negative 1/3. Now on the left-hand side, as I remove these parentheses, I get negative 3 times negative 1/3. Those exponents multiply. What's negative 3 times negative 1/3? Yeah, just to the first power, so I just get x. X to the first power. And then here, well, what am I going to do there? Take out your calculator, of course. All right, so let's make our calculator earn its money. I want 0.001 raised to the negative 1 divided by 3 power. Now, if your calculator doesn't, when you hit the raise key, the up arrow key to get the exponent, if it doesn't put you up into the exponent, if it gives you a little caret, then you're going to have to use parentheses around that. So this should give you 10. Y'all able to get 10 off your calculators? Yes? Darnisha? Okay, thank you. Good. And that's it. That's x equal 10. That's your answer. We're done with that one. I think it's what's called a QED. Sometimes in writing math books, proofs go on for pages and pages and pages. And you kind of got to like smack the reader a little bit and say, hey, pay attention, we're done. You're like, oh, really? And the abbreviation stands for quod erat demonstrandum, that which was to be demonstrated. It's a Latin thing. But in this class, you can remember it a little bit easier. It's quite elegantly demonstrated. All right. It's right here, guys, right here. All right, yeah. Got to practice that a little bit more. Yes. That might be. That might be, yeah. Make sure you get the problem right. But yeah, QED on the test? Sure. Yeah. It's because when you're writing a math book, some of your more advanced ones, the proof of something goes on for pages. And it's just kind of an alert to the reader, like, okay, we proved it. We finished. That's what we're trying to show. That's what was trying to be demonstrated. Quod erat demonstrandum. So it's Latin. So after this class, you go to the registrar and ask for your 1 credit of foreign language. All right. Let's try another one like this. So I said we're going to do problem 68. Let me follow up on that. Log base x of, no, that was 62. Log base x of 1/1000th equals negative 3/2. But the idea here is just like it was in 68, or in 62. So try and match your work in 62. Get a nice calculator solution. So we'll start out like we do a lot of these things. Rewrite it equivalently using exponents. So it's going to give me x to the negative 3/2 equals 1 over 1,000. The reciprocal of negative 3/2 is also going to be a negative number. Which negative number? Negative 2/3. So I want to raise both sides to the negative 2/3 power. On the left-hand side, a number times its reciprocal always gives me 1. So I get x to the first power, or better yet, just x. And then on the right-hand side, I'm going to do this on my calculator. Now, the one place you can go wrong is if you're trying to enter a fraction and work with it, and you don't use parentheses. So I need parentheses around that 1/1000th raised to the negative 2 divided by 3 power. Bam. Now, if your calculator is kind of old school, if you got one at home that doesn't do exponents like we're getting up here, then it would look like this. Raised to the power is going to show up as a little up arrow caret, and then you would definitely need parentheses around both of those terms in the exponents, or all three of them really. So again, you're going to get 100, but just be careful if you got an older calculator. So the answer was 100. Most of you guys get that one? Yay, give yourself a round of this. Yay. All right, thank you. A couple more to finish things up with. Let's try problem number 92. Log of x equals 2.8945. Well, how are we going to work on this one? What are we going to do? Oh, yeah? Excellent, 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 excellent. Yeah, we've got to remind ourselves that the base, even though it's not written, is 10. And boy, if you put that 10 there, this problem all of a sudden becomes very, very doable. So from here, we can rewrite it using exponents. Sharon, what would it look like if I rewrote this one using exponents, please? So what to what power equals what? Maybe some help? Yeah, 10 to whatever decimal there equals x. Now there's two ways you can get 10 to this power off your calculator. There's the brute force approach of writing 10 raised to the x, or in this case 10 to the 2.8945. Getting that. Let me go back to my other mode, which is the math print mode, because I like the way that prints better. Quit. Come on. There we go. You can press the clear key or second and then quit. So there's a couple ways to get out of that math mode. The other possibility for yourself, because 10 to a power occurs kind of often, you'll see it right above the log key. And that makes sense because the inverse of the log function is, an exponential function, in this case 10 to the x. So if I hit the second key, then the log key, again, it'll give me 10 to some power. I'll just type it in. Bam. Now they ask us to round this to the 4th decimal digit. Yeah, did I mistype it the second time? Yeah, I did. Because I was looking at that and going, wait a minute, that didn't give us the same thing. So, yeah, just go back and correct that. That's 8-9, not 8-6. Just missed it by a little bit. So if they ask us to round it to the 4th digit, it'd be 3, 2, 2, 1 there. So 784.3321 was what I'll be looking for. Make sure that if I ask you to round it to a specific digit, that you take care in doing that, because usually I allow 1 point of credit for rounding properly. How are we looking on that one? Well, I guess it's kind of implied to be a 1 here. It's not really written, but it's understood to be a 1. So, yeah. Let's actually graph the logarithmic function. So we'll do a couple simple ones. We'll start by graphing log base 2 of x. So this is going to be on the back side of your handout. That's what you want to grab for yourself. So we're going to graph y equals log base 2 of x. And the problem with graphing this is, it's hard to come up with easy, friendly points. So let me rewrite this. Log base 2 of x equals y. And then rewrite it one more time. This time I want to write it with exponents. So, Taylor, what would this look like using exponents? What to what power equals what? Good. Equals. Perfect. Thank you, sir. So 2 to the y equals x. Notice that in writing it like this, that you've got x solved for. You've got x by itself. Usually when we graph things, we plug in values of x and then get values of y. But since I've got x by itself, how about if we reverse the roles on that? How about if we plug in values for y and get values for x? Sure, works kind of the same. So let's give ourselves some easy points. 2, 1, 0, -1, and -2. So some easy points for y. We'll start from the bottom up. If I put in 2 for y, what do I get for x? Somebody said it. 4. How about if I put in a 1 for y? What do I get for x? 2? 0? What's anything to the 0 power? 1. And how about 2 to the -1st power? I don't want to leave it like that. What's another way to write 2 to the -1st power? 1/2. And finally, 2 to the -2nd power. Somebody simplify that for me. 1/4. Good. It's 1 over 2 squared, but that'll simplify to 1/4. So let's graph these points. See what they look like. You can add a few more if you wanted to, like a 3 and an 8. But we'll start with the easy points, starting with a 4 and a 2. So 4 for x and 2 for y. And then 2 for x and 1 for y. 2 for x, 1 for y. 1 and 0. 1/2 and -1 is going to kind of be between that. And then really got to stretch and squeeze to get 1/4 and -2. Now initially our chart didn't go out quite so far, but you can go out to 8 and 3, and indeed 4 and 16, or 16 and 4 I should say. But that gives me enough points. Gives me a nice graph. It's just a matter of playing connect the dots. So you get something that looks like that. And that's a graph of y equals a log base 2 of x. That's it. Yep, just it. There is one thing that I'll draw your attention to in the next section, but we can kind of see it here. And it's the domain of this function. Domain. Remember, the domain is which set of values? The x values or the y values? The x values. The x values start kind of right here on this line at 0. And they go up to infinity. So 0 to infinity. Now, the one thing to keep in mind about this is that this graph never really touches the x-axis. Why doesn't it touch the x-axis? Because its inverse doesn't touch, or this never touches the y-axis, because its inverse never touches the x-axis. The range would be negative infinity to infinity. And Cole, you're asking about extra credit points. You can write that as a script R. Let me try and write that again. Like here. Script R. That's all real numbers. So nice. Nice. Looking good on that one. Any comments or thoughts on these last few calculations or graph? Looking good there? Let me give you some homework then. Homework. 23 through 33, 39 through 47, 51 through 71, 75 through 81, 91, and 93. Does that look like a lot? Yeah. Really, they're considering that this is just the odd problems. There's only, I think, 26 problems there out of 138 problems in this section. So it's about a little over 1/5. Okay, cool.